Okay, consider simply supported beam. This is our simply supported beam given in the figure below. Find, filled out. Okay, so these are node 1, no, element 1, element 2. Okay, 2 we are having 2 element, and node 1, 2, 3, 4. Total we are having 4 node and 2 element. The beam is subjected. Okay. The beam is discretized into 2 beam element with degree of freedom given by red arrow. Okay, these are degree of freedom. These are degree of freedom. So each node having 2 degree of freedom. Formulate the global stiffness and mass matrix and global load vector. Okay. Apply the boundary condition and solve the eigenvalue problem to obtain eigenvalues and eigenvector. Okay. Ignoring the effect, necessary effect. Okay, that's fine. Given assume E equal to this much, Poisson ratio this much, density this much, beam cross section area. Okay. In the solution box provided given below, similar question they are going to ask. Same to same like this. In the solution boxes provided following value in the sequence. First, 2 eigenvalue after arranging the eigenvalue in ascending order. First, mass normalized vector, global force vector, element this of the lower triangular matrix L. Yes. So now you have to you are having 5 minutes. So just go through and try to solve. How we are going to start, then I will start. So you gone through that beam element, right? Yeah, you can check this. No. So you know what is beam element, how to find stiffness and final global stiffness of final stiffness matrix for any beam element. I think that one you already know. Now you have to find the eigenvalue. You want to try or should I start solving? Okay, then I will start. So just go through. I will add some page. Okay. So first, how we are going to start? First, I will write all the given parameter what they are saying. So they are saying it is having total 2 element. Sorry. So 2 element. And then each element having 2 degree of freedom. That's fine. So total number of node. Total number of nodes. How many? We are having total 1, 2, 3. Total 3 node. So I think you remember I told you that total number of node multiply by like each node like degree of freedom for each node. that will be our stiffness, overall stiffness, that size. So the overall global stiffness matrix size, what will be? It will be 2 into 3 equal to 6. So our global stiffness kg will be 6 cross 6. And how we will find? We have to add stiffness of element 1 plus stiffness of element 2. Okay, then these, or then the that we have to add, like vector we have to add. So now, but first we have to find the element stiffness matrix for 1, then element stiffness matrix for 2. Okay, then we will go here. So first I will draw here again that solution. So this much information I just wrote here, because that one we are, this is like thumb rule that we have to think, because if we are solving, like for example we are getting stiffness 7/7, it can't be possible. So this one we have to first we have to write that number of element, number of total node, and each node having this much degree of freedom. Then our final global stiffness size will be 6 cross 6. So okay, so this first element having how many node? So how many node? Yeah, it is having 2 node, like this much, node 1, node 2. So what will be stiffness size of this node, this element 1? What will be stiffness matrix size for element 1? Tell me. Are you here? It will be 4 cross 4. Yes. So first I will draw this again here. It will be 4 cross 4. So this is our beam. So it is having node 1, node 2, node 3. This is distributed load. Element 1, element 2. We are having 2 elements. Then how many node? Node 1, node 2, node 3. So total we are having, I will write like node in another way. So node 1, node 2, node 3. So these are nodes, number of nodes. These are number of element. So we are having total three node and 2 element. Okay. So we will start with first element. So first element we will take. One more thing I want to write here. I will write first element. Element number 1. Element number 1. So each node having 2 degree of freedom. How many? That vertical or the rotation. So each node having vertical rotation, vertical rotation, vertical rotation. So for example, yes. So for example, for this node 1, I will say this is B1 and this is theta 1. For node 2, this is B2, theta 2. For node 3, B3, theta 3. What is B3? B means vertical or we will say translation displacement in bidirection. Then theta is the rotation about z direction. Yes, this much yes. Yes, no. So now what we have to do. So first we have to find stiffness matrix for first element, then second element. Then after finding both stiffness matrix, we are going to add, or we are going to sum up. Then we are going to find the final global matrix for this whole system. Then what will be first element stiffness for element 1? We know that formula. What is the formula? So stiffness अरे मेरी कमर दर्द होने लगी. So stiffness matrix for first element. What will be stiffness matrix for first element? We know formula. What is the formula? Element stiffness matrix for any element. So I will write first equal to. We are having ready-made formula. EIY LQ and 12 6 L minus 12, then 6L, 6L minus 12, 6L, 4L square minus 6L, 2L square, then minus 12 minus 6L and 12 minus 6L, and again 2L square minus 6L, 4L square. So I will say this is elemental length E, 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 E. Okay. Then where what is E means? E means the Young modulus equal to Young's modulus. I is the what is the area moment of inertia. Area moment. Then L is the length of element. I think this much you understood that what actually means of this stiffness matrix. So this one you have to remember. This one 12 6 LE, then this 12 6 LE minus 12 6 LE 6 LE 4 LE. Just what you can say, remember to best way, like this is symmetric matrix, then what will be size will be 4 by 4. Why 4 by 4? Because this yeah, I will write here. So first element I will say I just want to copy this one down. I want to take it down. Yes. So for first element, I will write here like this. this is our first element, or any element. It is having length L, LE, and having node 1, node 2. So each node having 2 degree of freedom, theta 1, B1, theta 2, B2. So what will be our that displacement matrix? So it will be look like U for element equal to, it will be like this. It will be like this. B1, theta 1, B2, theta 2. Okay. Similarly, if I am saying at each node having two load, so first like if I saying load, like for example, this is M2, F2, then similarly M1, F1. So force vector, how will we write force vector for element? It will be F1, M1, F2, M2, where F the force in vertical direction, and M is the moment about Z. I think this much okay, just basic, right? Yes, yes, no. So that one you know, right? Initially, you know, I think this one you know. Okay. Now you what we have to do. This is our first stiffness matrix. This is our stiffness matrix for first element. Okay. So what we will write? We will write here our element having this is our element. Okay. So this is our element. This is our element like this. It is having 2 degree B1, theta 1, B2, theta 2. So how I will write? I will write here B1, theta 1, B2, theta 2. Then here also B1, wait 1 minute. I will take this one down. This is also, I will make very small, not required that much. Take this one there. And so what we have to write here, this will be our theta 1, sorry, this will be our B1, theta 1, B2, theta 2. Similarly, B1, theta 1, B2, theta. Why I am writing like this? Because when we are going to find global matrix, then we have to add respective degree of freedom at each node. Okay, so this one done for first element. Now we have to put value for all the given parameter. So we are having E equal to 300, then length, what is the length? 2 meter. So it will be L by 2. I think there is no, okay, that you can do that one. For second element, now we are similarly for similarly we have to find mass matrix. So mass matrix for second element. What will be mass matrix? So I will write here mass matrix for element 1. Sorry, first element only, not second. Sorry. Element will be for first element. So we are going to find a stiffness and mass matrix for each element. So now we are going to find mass matrix for first element. What will be our formula? Rho A L element by 420, then 156, it will be 22 LE, 54, 13 LE, 22 LE, 4 LE square, 13 LE, 3 LE, element length, LE means element length, then 54, 13 LE, 156 minus 22 LE minus 30 LE, this will be 3 LE square, 3 LE square minus 22 LE 4 LE square. So this is the mass matrix for any element that is having 2 degree, first one vertical, other one rotation direction for beam element. Okay. So one thing I want to tell you here, these are the, what will you say, it will be 4 cross 4 same. These are the symmetric matrix. So you can check, these are symmetric matrix. So if I draw one triangle here like this, then you can see that this is the symmetric matrix. See, like minus 12, minus 12, minus 12, minus 12, then 6L, 6L, 2L square, 2L square, minus 6L, minus 6L. So this will be symmetric matrix. So I will draw here like this. One triangle, it will connect like this. So you have to remember this triangle element, rest you can find because these are the symmetric matrix. Symmetric matrix. Okay. Similarly, for in this mass matrix also, you have to remember these elements. So, for example, if I will say like these are the 1, 2, 3. So this is like this is 3, 1. 3, 1 should be equal to 1, 3. Yes, this is equal to 1, 3. And if I will say, what is this? 4, 2. 4, 2 should be equal to 2, 4. So just check 2, 4. 2, 4 means 2, 4 means this one. These are same. So are you getting right? Good. So now after calculating the stiffness mass matrix for each element, as of now we calculate for only first element. Here also I will write similarly that theta 1, this is our B1, theta 1, B2, theta 2, B1, theta 1, B2, theta 2. Here now similarly for second element. So now I will write again here second element. So I will use technique. I will just copy this one, copy, and I will paste here. Right. I'm going to copy. But you cannot copy paste. Copy. Oh, sorry. So now for second element, how we are going to similarly for second element, I will write here. So this is for first element. First element. And I will request you, when you are solving exam, any other exam, when you are solving these type questions, write first element, second element, third element separately, so that it will not mix up. Then this is for second element. Second element. But what we have to remember here, for second element, we are having different degree of freedom. So I will draw, because this element, this one, this is our second element. So it is having theta 2, B2, B3 and theta 3. So that one we have to update here. So for second element, so this will be, we have to remove this one, this. Similarly here. Yes, okay. So this is our second element like this. So it is having first, second. So it is having B2, theta 2, and this node having B3, theta 3. So this is node 2, this is node 3, and this is our second element. Okay, so it will be B2, theta 2, then B3, theta 3. Similarly, B2, theta 2, B3, theta 3. Here also B2, theta 2, B3, theta 3, B2, theta 2, B3, theta 3, and this one also we have to update. So it will be K2. It will be K2, M2. Till now, you have any doubt? So are you getting, or you know initially how we are going to solve? If you know, then we will go a little fast. Eh? We should go a little faster. This is okay. Yes, no. Then okay. So now after calculating stiffness matrix for each element, now we have to find the global stiffness matrix. So as of now, what we are having two stiffness. These are called local stiffness. I will write here. So these called local stiffness. Local stiffness. And these are the local mass matrix. Stiffness matrix. These are local mass, local stiffness, and similarly this local, and this is also local. So we are having two stiffness matrix, that is in local direction, local stiffness, and two mass matrix. So now what we have to do? We have to find global mass and global stiffness. What meaning of global? Global means for that will represent this whole system, this whole beam system that will represent. Right now, what we are having separate stiffness mass for this element and separate stiffness mass for this element matrix. But we have to find global mass and stiffness. It will have one mass and one K. Right now we are having two mass. So after adding, we will get only one mass stiffness matrix, one mass matrix, and one stiffness matrix. That one I told you here. Like first element having K1, second element having K2. So after adding these two matrices, we will get one global matrix. What will be size of global matrix? It will be 6 cross 6. But these local are having 4 cross 4 size. Yes, no? Yes? Yes. So these local matrix having size 4 cross 4, but the global matrix size will be 6 cross 6. How we get to know that it will be 6 cross 6? Because we first find how many nodes it is having. Total 3 node. It is having total 3 node, and each node having 2 degree of freedom. So 3 into 2 will be 6. So 3 into 2 it will be 6. So after writing these two lines, we get to know that the size of global matrix will be 6 cross 6. But the size of local matrix for each element it will be 4 cross 4. Because why? Because each element having two nodes and each node having 2 degree of freedom. So 2 into 2 will be 4. Yes, I think as of now everything clear. Okay. So what I will write now, we have to find one global matrix. So what we have to do, I will just copy this one from here. This is our stiffness K1. This is our K1. I need a little smaller. This is our K1, and this is our K2. This is our K2. Okay, so this is our K1 and K2. Now how we are going to add, how we are going to find the global, that I am going to explain here. So, okay, this. These are local, okay. Now, so just first you have to remember, you have to check here that which node is common between these element. So if I draw element here, so this is our actual element. This is our full node 2, yes. So 1, node 2 is common. 1, this is second node, this is third node. So this is node 2 is common node. Okay. So but we written that this node having 2 degree of freedom, that B2 and T2. Sorry. B2 and theta 2. So this is B2 and theta 2. It is having 2 degree of freedom, that is common. So what we have to, how we are going to add that whatever degree of freedom are common, we have to sum up for each element. For example, at this for this element, one extra element added like this. So here one degree of freedom shared by 3 elements, right? The one node is shared by 3 elements. So at this node, we are having like theta 2 and beta 2 that we have to add for all 3 elements. I think element 1, 2, 3. All 3 elements we have to add. I think this one you got what I'm trying to say. That for common node we have to add the degree of freedom in respective direction. Yes. Yes, just you can say yes or no.
Sir, I think this part I'll understand while doing the sum, sir.
Why we are doing sum up, eh?
Sir, I didn't understand.
Why, what are you saying? You are not understanding why we are
So,
doing sum,
so,
eh?
so this extra you said no, sir, to add extra something node or something like that. That part I didn't understand.
Okay, so listen. Like for example, just forget about this one. I am having this. This is node 1, node 2, node 3. And I am adding here one extra element, which is having node 1. So element 1, element 2, element 3. So at this node shared by element 1, 2, and 3. So this node is shared by all 3 elements. This one also, this one also, this one also. But what we are saying that each node having 2 degree of freedom. So this is having like this theta 1, theta 1, beta 1, theta 1. This is also having beta 2, theta 2. This is having beta 3, theta 3. Then uh, beta 4, then theta 4. So if I will say for this element, first element I will draw like this here. First element, it is having node 1, node 2. And then second element, it is having node 2, node 3. And third element having node 2, node 4. See, this node, it's common in all these 3 elements. Yes. So what will be actual displacement at this point, that we have to add whatever we are getting from different element. That I am trying to say. Like for example, actual displacement will be sum up of these all. Like for example, this structure moving in like for this, it is moving downward direction. So it will like it is having some effect on for this node, this element having some effect at this node. This is also having effect. This is also having effect. So overall effect we have to add. I think now you got okay, na? Hopefully. And you got to just you. I should I explain again. Okay. So now what we are going to do? Mm, I will just copy from this one. Cut. Okay. So now this node is common. This node is common between both element number 1 and element number 2. So the degree of freedom at this node, or we have to add, in another way we have to add the coefficient of stiffness, even though mass also be, for all these stiffness whatever we are getting metric we have to add at this location. Then how we are going to add, that I am going to explain. See, so this one, see, uh, these are affected like theta 2, theta 2, and this one beta 2 and theta 2. This much area. Similarly also beta 2, theta 2. That we have to add. Now what will be our, this is having size 4 cross 4. This is also 4 cross 4. And how we are going to find global matrix? What will be our global matrix? It will be K G equal to global equal to 6 cross 6. It will be 6 cross 6. Okay. Then for global matrix, what will be our that coefficient? So it will be like B1. Very less space. I will write small. So this is having Kg equal to, it will be 6 cross 6. It will be B1 theta 1, B2 theta 2, B3 theta 3. Like that we have to write here. Then similarly here also B1 theta 1, B2 theta 2, B3 theta 3. So we will have this much, like 6 row, then 6 column, 6 column, 6 row. I will give this one bigger. Like this. Okay. Like this. Total, how many coefficient will be there? Can you tell me? Total, how many coefficient will be there in this global matrix stiffness? Hello? I'm telling you, I'm asking to you. No. Like coefficient, stiffness, what will be the number of coefficient? Number of coefficient in global stiffness matrix. It is having 6 by 6 sides. Total will be 36, na? Coefficient means like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, up to 16. 36, up to 36. So 6, it will be 36. So now how we are going to find that global matrix? So what we have to do now, we have to check that B1, yes, then we will put B1 at this location. Okay, then theta 1 B1, so theta 1 B1 we will put that this location. Correct, like this out. Yes. Then beta 2, sorry, B2 B1, so B2 B1 it will come here. Then theta 2 B1, theta 2 B1, then B3 B1, but we are having B3 and B2, so they will be 0. First I'm just trying to explain. Then similarly for that B1, then okay, this row, then B1 theta 1 for second row, so B1 theta 1 it will come here. So and these point we have to add. Okay, now I'm going to find that I'm going to assemble and I'm going to add these two matrices. What will look like? So what will be actually? Then I will copy all these things. Copy and paste here. Okay, then I will delete this one. This one also. Then these things also I will delete. Okay. So what will be our global final global matrix? This one also I will delete. Okay. Then one thing we have to think here that this one will be deleted, and what will be our final one? Because we have to add at this location. What will actually will happen? It will come here like this. This one completed. This also we will delete. Doing like this. But I have to write here. Unnecessary I am doing. Okay, that's fine. Wait, I will just explain you. So it will be our kg equal to, it will be like this. So b1 theta 1, b2 theta 2, b3 theta 3. Similarly, b1 theta 1, b2 theta 2, b3 theta 3, and this one like this. Kg. And actually these elements having length 2 of this is a length 1, this is length 1 element length, and these are element 2 length, and this one we have to add. Remaining it will be 0 0 0 0 0 0 0 0. This one we have to add. What will be here? That these two part will be added. These two part will be added, and here also like this whole term will be multiplied by E L and that EI by element length 2 square. So are you getting something? Or should I, because this is having a different length now. So like that we have to add. Or should I write like in simple way? So these point, what I'm saying, this these two by two matrix we have to add, and this matrix will come here at this location, and remaining point they will become 0 because the B1 don't have any effect at theta 3, so this will be 0. What I'm saying that this degree of freedom, yeah, this degree of freedom don't have any effect at B3, so it will be 0. But this degree of freedom having effect on B2, but this will not be 0. Okay. Similarly, theta 3 don't have any effect on theta 1. So 1 3 will be 0 and global matrix. So 1 and 3. What I will say? Theta 3, like B1 and theta 3. So B1 and theta 3. B1 and theta 3. This will be 0. Similarly, B1 and theta 3, this will also will be 0. Yes? Yes, sir. Okay, hopefully you got. Then similarly for mass matrix. Now we completed this. This will be our 6 cross 6 stiffness matrix. Similarly, we have to find for mass matrix MG, global mass matrix. Then what will be elemental stiffness matrix for 1, then elemental stiffness matrix for second element, it will be 2. Then we are having different similarly. So these two element or these four element will be added to this our first what I will say, first element last four mass matrix element coefficient will be added to for second element first four mass coefficient. Yes, like this we can say. So this they
Yes,
will be.
hello. Hello.
Yes.
Sir, this mass matrix will be similar for that, sir. So both the elements, because so second element is having UDL, no, sir. So it won't vary, no, sir. It will be standard.
I didn't get what.
Sir, mass matrix will be similar for both the element, like for.
It is standard only. Yes.
Okay.
Mass, stiffness, damping, everything will be same for all the element. But only what we have to remember that we have to, when we are finding global, we have to remember which element which coefficient we have to sum up. That thing only we have to remember.
Okay, sir.
Okay, na? So because these are like standard metrics for mass for this element. Stiffness also, these are standard only. But just we are adding at that common node. Okay.
Okay, sir.
But the problem isn't solved. Now what we have to do, we have to put all the that length, e row, every all the that value we have to put, and we have to find finally global matrix. Can you try that one? If you have that calculator. Yeah, please try. And then I will confirm it is wrong or right. So what will be now? So these are our elemental mass, elemental mistake, elemental stiffness matrix. So please tell me what will be our final global matrix after putting the value. So after putting the values of all the given variable. But don't forget one thing, that whatever length we are giving here, that length, it is having L by 2. So for first element, we are having length L by 2. L having br 2, so it will be only 1. That we have to remember. Then what will be after putting the value of all the given variable, then kg, like first global mass matrix. So I will write first global stiffness matrix, and then that one we have to add these. We need to add. We need to add. And similarly for that mass also. So these four. We need to add. So what will be first global stiffness matrix K, and its size will be 6 by 6, and second one global mass matrix M, it will be 6 cross 6. I will write kg and mg. Yes, please tell me. Here, see, length is same. See, in given problem, length is same. So K1 and K2 will be same. M1 and M2 will be same. Right? Because length of my element is same, only L by 2. This is L by 2. So but K1, K2 will be same only. M1, M2 also will be same. Note, I will write one note here. If length of elements are same, then matrix will be same. So here K1 will be K2 equal, and M1 will be M2. So please tell me what will be our final stiffness matrix and final mass matrix. That one we have to find. Hello, hello. Are you here or you are sleeping? Okay, okay. So please tell me what will be because these type question they are going to ask, but not that much simple. They will say like length is same. So just you have to find one stiffness, then it will be equal to second also. Then just you have to assemble. Then you have to put that. Then you have to, after assembly you will get the global matrix. After getting global matrix, then you will move further on for that question. Then they will have different type. Maybe they will have for displacement, load. That is separate. First, I will just try to verify what will be your first K1 matrix. So K1 will be, because everything given that K1 will be 8 3 3 3 3 3.4 S. Then 12 6 minus 12 6 6 4 minus 6 2, then minus 12 6 minus 6 2 12 minus 6 minus 6 4. This will be your K1. Similarly, K2 will be same, so it will be 8 3 3 3 3 3.4 12 6 minus 12 6 6 4 minus 6 2 minus 2 12 6 12 minus 6 6 2 minus 6 4. This will be your K1. So what we have to do, we need to add only these point, these coefficient. So we will get their final global stiffness. It will be look like Kg will be 12 cross 12. So okay, wait, I will have down here. So our Kg will be it will be 12 by 12. Then similar 8 4 and 12 6 minus 12 6 0 0 6 4 minus 6 2 0 0 minus 12 minus 6 24 0 minus 12 6 6 2 0 8 minus 6 2 0 0 0 0 minus 6 12 minus 6 6 2 minus 6 4. So are you getting this like this? and these one we have to add. These three will come where? Here. So did you got like this? This will be our 6 cross 6. Okay. And similarly, what will be mass matrix? I will write here. So M1 will be 0.0934538. Then it will be 156, 22, 22, 54, and 30, 4, 30, minus 3, 54, 13, 156. Minus 22, 4 plus 4. Similarly, M2 will be equal to M1. It will be 38. And this matrix copy paste like this, and we have to add these two row and column with this one. Sorry, that one we have to we need to add. That will be final global mass. Mass matrix. What will be global mass matrix? I will just copy from here this thing, paste here, and then again I will paste here, copy this one, paste here, and this thing going trader. So this will be your global mass matrix. It will be 0, 0, 0, 0, 0, 0, 0, 0, and each point we have to fill. What will be here? 3, 1, 2, 3, 1, 2, 0, 0, 8. Okay, like this. It will be 6 cross 6. So just you can verify once, like you are getting same thing. And this one, we have to come here. Shri Ram. That good. Mass matrix also correct, right? Mass and okay. So now after calculating these two big matrix, they could like these type question they are going to ask definitely in your exam. So we started from here this big solution. So now we have to find the and that okay. Now what is the boundary condition? We are having boundary condition. Our element beam. Yes. So boundary condition. Boundary condition at here what will be that displacement will be 0, okay, but theta 1 will not be 0. At this node displacement 2 will not be equal to 0, theta 2 also will not be equal to 0. At this location displacement 3 b3 will be 0, but theta 3 again will not be 0. So what we can say there from these boundary condition that we are getting displacement at node 1 0 and displacement node 3 also equal to 0. Okay, so displacement at node 1 and 3 say b1 and b3 equal to 0. That one we have to remember, and I will just take this one copy. So I will add few more here. Whatever bounding what we got, is what is copy from there. The displacement and these 3 degree of freedom is 0. So this is from boundary condition. This is from boundary condition. So now applying boundary condition b1 equal to 0 and b3 equal to 0. Now we have to eliminate that respected row and column. Okay, so what I'm saying, we need to eliminate respected rows and column corresponded to fixed boundary condition. So here B1 and B3 0. So what we have to do? So from our global mass and stiffness matrix. So I just copy from here. So this is our global stiffness. Global stiffness copy. Yes, this is our global stiffness matrix, and we have a global mass matrix. This is our global mass matrix. So what we have to do? This is our global stiffness. This is global mass. So what I told you, that we have to remove respective row and column. So B1 and B3. So I will write here. This is also 0. 1, 2, 3, 4, 5, 6. Here 1, 2, 3, 4, 5, 6. Then okay, not like this. Sorry. We are putting not 1, 2. We are putting only B1 theta 1. So it will be B1 theta 1, B2 theta 2, B3 theta 3. Similarly, B1 theta 1, B2 theta 2, B3 theta 3. So we are having degree of freedom B1 and B2. We have to delete. So this is row, this is one column. Similarly, so this one will go, this one will go. Then B3. So this one will go, and 1, 2. Then here also we have to write. It will be B1 theta 1, B2 theta 2, B3 theta 3. So this one will go. Oh, are you getting what I'm doing here? Yes, okay. So similarly for mass matrix also, we have to remove the respected row and column. So this row will go and this column will go. Similarly, this column and this row. Yes. So what will be remaining final? What will be again? Final will be our. I will write here. So kg will be our final. What will be kg? 8 3 3 3 3 5 by 3 into 0.4. It will be 4 minus 6 2 0 and minus 6 24 0 6 2 0 8 2 0 6 2 4. And what will be our mass? Mg will be 0.093452338. Just you also will verify. I will ask you again. So just check I'm not doing anything. Should I not do anything wrong? So I will ask you to verify. So you can also do from your side. 0, 13, 3, 1, 2, 0, minus 13, minus 3, 0, 8, minus 3, 0, minus 13, minus 3, 4. So just verify once it is correct. Please verify it is correct.
Sir,
Hmm.
that below 4, no, sir. So first row, second column. Sir, second row, first column. So there is minus 13, no, sir. So below
Mass,
4.
mass or that
Some mass, mass. Some mass wala.
this plus it will be plus, na, right?
Yes, sir.
Ah,
13, yes.
sorry. That means you are not sleeping. That's good. It
No,
will be.
sir.
So this is correct. You are getting something right.
Yes, sir.
Now, now we have to find the that what we had the question. We have to find that eigenvalue. So first eigenvalue after arranging the eigenvalue descending order. We have to find first two eigenvalue. So first two eigenvalue we have to find. So how we are going to do? Then you can write your MATLAB code, and also you can use some that if you are going for MATLAB. So what we have to do? You know MATLAB, right? A little bit. You have MATLAB in your system right now? No, sir. Okay, listen. So now what we have to do? I will tell you what in MATLAB. In MATLAB, or I will show you just a minute. So what we have to write? We are having one command that phi, then lambda, uh, lambda equal to EIG means eigenvalue. EIG means eigenvalue. Then k comma m. So what will be here? Phi will be our mode shape, and lambda will be square of square of eigenvalue. Actually, what is eigenvalue? Eigenvalue represent the actually natural frequency of system. And what is a mode shape? What is phi? Phi also called eigenvector. So we are also calling it eigenvector. And what is eigenvalue? Eigenvalue means natural frequency of system. That's why we are doing this much long this schedule. So what is the nuts in nutshell? After calculating mass and stiffness matrix, we have to find eigenvalue and eigenvector. Okay, so what eigenvalue? Eigenvector means mode shape, and eigenvector means mode shape, and eigenvalue means natural frequency. What is natural frequency? That what like natural time period, all these things. And what is mode shape? Mode shape means, like for example, how the structure going to behave in natural condition. So I think you went through the structure dynamics. They told you about what is mode shape and natural frequency. Yes. Yeah, that no. Yeah, this is very long question. So now I will go through MATLAB, then I will tell you how to find that natural frequency. So 1 minute, I will present my screen again. Exit. Okay. So this is from for today from this side. Similarly, now we are going to solve this problem by using that MATLAB. How we are going to start? First, we have to put that our given stiffness matrix. This is our stiffness matrix that we have to provide. This is our mass matrix. So I will write here. This is our stiffness matrix, and below is this our mass matrix. Okay. So now we have to find that eigenvalue and eigenvector. So now finding the eigenvalues and eigenvector. So in MATLAB, we have to give one command that where phi is the eigenvector and lambda the eigenvalue, and ei is the command that we have to provide, and k and m is that stiffness mass matrix. Then but after running this, what we will get? So now we are going to run this one. So we will get lambda. These are the lambda that lambda 1, lambda 2, lambda 3, lambda 4. We are getting 4 lambda because we are having 4 by 4 matrix mass or stiffness. Similarly, this is our eigen vector. So phi 1, phi 2, phi 3, phi 4. So now by using simple this MATLAB, we can get the easily eigenvector and eigenvector and eigenvalue for any system. Then yes. So then if you want to find that natural frequency, so natural frequency will be square root of lambda. So it will be square root of lambda, and it will come in radian per second. Radian per second. And if you want to find natural frequency in that hertz, so what we have to do? Omega equal to 2 pi f means 2 pi equal to the natural frequency of that natural frequency in radian per second divided by 2 into pi. So we will get the natural frequency in hertz. Okay, then if you run this one, what we will get after running this one? What we will get? Sorry, this is your lambda, LAMB. So if I will run this one, what we will get? This is our natural frequency. Natural frequency or natural frequency in radian per second. So this is our in hertz. This is our natural frequency in hertz, and this is in natural frequency of radian per second. So like that, you can get the natural frequency in, for any system. So just if I will say this mass matrix on this right now, this is 4 by 4. If I will say this mass matrix or stiffness matrix is 10 by 10, just we have to put that value here, this matrix, and it will easily will provide the that natural frequency that eigenvalue and eigenvector for any system. So like this we can solve that. Just we have to remember this command eig, eigenvalue. That command will provide the eigenvalue and eigenvector for any system. In our that structural dynamic in way, eigenvalue is the square root of natural frequency is the square root of lambda eigenvector eigenvalue, and phi means mode sieve is this phi. Okay,